All right. People online, if you can hear me, please say something.
Anyone on provision?
All right. Great. Thank you. Okay. 9 o'clock. So let's get started. Today we are going to up ahead. We'll review summation notation, which we talked. Sorry, my phone. We'll review summation notation, which we talked about last time. Also geometric sequences. I think we've done enough with the general term partial sum formula, but we'll do a few examples with that infinite sum formula that we got to in the last class. And then we'll introduce, we had some time to talk about interest, but this time we'll actually look at the formulas and how those are connected to these two types of sequences that we have been talking about. And that should be it. So from last time, we'll just jump straight into it. Summation notation. If you remember it, take this thing and figure out what the sum is of this. Morning. All right, does anyone have an answer? You saw this last time. Anyone have a number for me? If you're online, you can write it into the chat. No one yet? This was meant to be the easy warm-up question. Yes, warm up. 13/36. Okay, let's check this. So first, in this thing, how many terms will there be? Okay, where are we starting? 2. When k is equal to 2, our index is equal to 2. Each time we go up by 1, so 2, 3, and stop at 4. There are 3 terms to this. Yes, usually we start at 1, but we don't need to. So make sure you read that number carefully. What is the first term here? 1/6. So 1/3 times k when k is equal to 2. 1/3 times 2, 1/6. What's the next term? 1/9. And our last one, 1/12. That's it, just those 3 terms. Adding fractions, convert these. Lowest common multiple is 36, so 6/36 plus 4/36 plus 3/36 is that. So we just added this manually. We just figured out each term and just added them together. We did have two formulas that we talked about. Would those formulas work? So first, is this an arithmetic sequence? No, why not? What is the condition for an arithmetic sequence or series? If we look at all the terms of an arithmetic sequence or series, there has to be the same something. Same what?
Same difference.
Same difference, the D value, common difference. We need to be able to add the same thing each time. Going from this 6/36 to 4/36, what are we adding or subtracting? Okay, so this is minus 2/36. And if we look at the next pair, well, that's minus 1/36. Not the same, not a common difference. Okay, next one. Is this a geometric sequence or series? Okay, what is our condition for a geometric? All right, our common ratio. We need to be able to multiply or divide by the same thing. Let's try that. So first term to second term, what would we multiply by? Two over 3. 2/3. So 6 divided by 3 is 2, and then multiplied by 2 gives us 4. So that's the ratio for the first two. What's the ratio for the second two? 3/4. 4 divided by 4 is 1 times 3 gives 3. Okay, so that's the ratio for that one. Not the same, so there's no common ratio, so this is not a geometric series either. So we have those formulas, but we should check and see, can we actually use them? You can't just like blindly use them and assume things will work out. So make sure you check, is it actually arithmetic? Do we have a common difference or common ratio? Or either one. Okay, next example. This one here. Take this and rewrite in summation notation. So that big E thing we just saw. And fill in the details. All right, let's see what we have. So on the bottom, where would be a good place to start? 1, okay. So I equals 1 and up to 5. So if this is 1, this must be 5 because we have 5 terms here, and starting at 1, 2, 3, 4. It looks like that'll work pretty nicely. What's the actual general term here? 1/i. So the sum of 1/i from I equals 1 to 5, if we want to make sure that we have this correct, just evaluate a few of the terms. So 1 over I when I is equal to 1, that's 1 over 1. When I is equal to 2, that's 1 over 2. And then okay, we can kind of easily see the rest of these. 3. 1 over 1 is just 1. So, okay, it's the same thing. We got our answer right. All right. Next. One more example here. Figure out the sum for this one. If you want to use a formula, make sure you know that you can use the formula first. Do we have a number? What's your answer? 52. All right, let's see what we get here. Before I actually start evaluating the terms, might be a little easier to simplify a bit. Can we take this thing here and simplify this? Okay, so we can simplify this 1 over 15, 5 to the exponent j. So 5 to the exponent j over 15. What can we do with the 15? Noticing that we have a 5 to some exponent on the top, we can split it up. So 15 is 3 times 5, right? Then we have our exponent rules, a 5 on the top, 5 on the bottom. So if we simplify this, it will be something over 3. Okay, 5 to the exponent j minus 1, like this. So it's a little simpler, a little nicer than that. Might be not huge difference, but something. So we could rewrite this like this: 5 to the exponent j minus 1 over 3, and just figure out what our terms are. So what is our first term? Just 1? This over 3 is going to have to be there somehow. 1 over 3. So 5 to the exponent j minus 1. So 5 to the exponent 0, that's 1. And then over 3 on the bottom. What's our next term? 5 over 3. Then it looks like it'll just be sort of powers of 5 on the top. So 5 squared. 25 over 3. And 125 over 3. All right, if we add up all of the things on the top, we get 156 over 3, and simplify that at 52. So in this way, how I've just done this, I didn't use a formula. Could I have used a formula here? Which one? Like which type of sequence or series is this? Okay, this is a geometric. So partial sum for a geometric series with this information here, this would work. What is the R value? 5. So this 1 over 3 times 5 gives us 5 over 3. 5 over 3 times 5 gives us 25 over 3, like that. So that's all the information we would have needed. Also, when we look at this, if you have some constants to the exponents of the index here, that's probably your common ratio. Double check, but that's a pretty good hint or clue that that's what it will be. All right. So next, just formulas. Take 2 minutes trying to write down all these formulas without looking at your notes, just from memory. See if you can do it. It's 2 minutes. If you know the formulas well, that should be plenty of time to write them down. Let's start here. Arithmetic sequence general term. What's this formula? A1. Okay. All right. So n minus 1 times d. We can switch the order of the n minus 1 and d. I'm just writing it this way because that's how we've always seen it in class, just for consistency. Partial sum for an arithmetic sequence. N over 2 times a1 plus a n. All right, and then we had the longer version of this if we just combine this with the partial sum. 2a1 and minus 1 d. All right, so I never actually gave you a formal kind of formula for the d term, but we can figure that out now. What could this be? A2 minus A1 works, but I want a more general version. Okay, yes, I'll just write this a little differently. So you said plus? Okay, so minus a n minus 1. So any term, subtract the previous term will give us the difference between the two terms, because a n minus 1 plus d gives us a n, right? So that's just from the definition of what the common difference is. So I don't know that we really need to kind of memorize a separate formula, but we should understand that that's true. Okay, so from this D formula here, what would our there we go. That's you guys are kind of mixing different versions around. A n minus 1 like this. So any term divided by the previous term will give us the ratio between those two terms. So A2 over A1, yes, but again, the more general version is a little more useful to remember. All right, general term for a geometric sequence. Okay, so multiplied by r to the exponent n minus 1. All right, and partial sum formula here. N over 2 is here for arithmetic sequences. Okay. So r to the exponent n minus 1. R minus 1 here. And then our other version of this, A1, 1 minus r exponent n over 1 minus r. As I mentioned in the last one, the last class, with the general term formula, the n minus 1, the whole thing is in the exponent. With the partial sum formula, only the n, the minus 1 is not part of the exponent. Very common mistake that people make there. We had these two versions. What's the difference between these two? Okay, so here. So this first one here, it's a little more convenient if our absolute value of r is greater than 1. This one, a little more convenient if the absolute value of r is less than 1, but both will work in any situation. It's up to you. All right, the last one that we saw at the end of last class. A1 over 1 minus r. And we talked a lot in the last class about why that works and where that formula comes from. I'm not going to repeat that today, but it's there. So very simple formula for the last one. So it is, or you tell me, when can we use this? What's our condition for this to be true? Okay, so if our absolute value of r is less than 1, so r is somewhere between 0 and 1, then this will work. But if our r value is greater than 1, this is not going to work. The sum will just be infinity or negative infinity. Okay, so there are the formulas, and we will have two more formulas with our interest, simple interest and compound interest formula. This is the formula unit. We don't have many of them in this class that we use, but we need lots of them for sequences and series. All right, let's actually use that infinite sum formula. I have two examples. This is the first one. Tell me what this would be. Figure it out using that formula. Everyone agrees? Yes? Okay, so let's just write out what some of these terms would be. What is the first term? 1 over 2. Next term? 1 over 4. 1 over 8. Okay. All right. So we see the pattern here. This is the question that I asked you for the preview homework. So we had that example from the last class. If I try to walk halfway to the wall and then halfway again, and then half of the remaining distance and on like that. So In the math world, it is equal to 1 when we go to infinity. Again, if you ask a physics person or like a natural chemistry or something, they will say it gets very close but never gets there. In the math world, we actually go to that point of infinity. We do reach that spot. So let's just practice the formula here. First term is 1 over 2 over 1 minus 1 over 2, which is 1 over 2 over 1 over 2, which is just 1. All right. This whole actually going to this point of infinity and then seeing what the number is at the end. This is something that we will be using with our calculus stuff as well. So not the only time we will see this concept. All right, so one more example with these. Ready? All right. This one as well. So use the formula and figure out what the sum is here. Say 1 over 9. The sum is 54 plus 18 plus 6 plus stuff. I think it's going to have to be a lot bigger than 1 over 9. All right, I think 81. Anyone else have a different answer?
84.
84. I heard infinity. All right. So if we're going to use that formula, infinite sum a1 over 1 minus r, we need a1. Well, 54, that's very easy. We need our r value. What is r? 1 over 3. Okay, so 18 to 6, divide by 3. Okay, 6 to 2, divide by 3. 2 to 2 over 3, divide by 3. Okay, so 1 over 3 looks like it works for our r value. So 54 over 1 minus 1 over 3. 54 over 2 over 3. If you want to remember fraction rules, inverts, multiply. 54 times 3 over 2. 54 divided by 2, 27 times 3, 81. So the infinite sum idea might be a little complicated, but if we understand the formula, then using the formula can be pretty quick. We only have 2 numbers to put into it, and it's a pretty quick calculation here. I forgot to mention, people online, my little microphone pack, I forgot to charge the battery. So if suddenly you stop hearing my voice, just like spam lots of messages in the chat, and then I'll notice, and I'll switch to a backup microphone. Okay, so interest is our next topic, our application of these sequences in series. We introduced or previewed kind of the ideas, just to remind you here. Interest, it's just like rent on money. You borrow more money, you pay more rent on that. It's calculated as a percentage of the amount that you borrow. So that's where all of our interest rates and such will come from. Okay, so terms we will need for this, which we had last time, I'll just go again. So lowercase I is our interest rate. Some textbooks will also use R. So this kind of common ratio we'll see in a bit. So you might see that some places. Interest, the actual dollar value of the interest is capital I. So lowercase I, capital I, different meaning here. T is just your time, usually in years. So let's say we have 2% interest and we have a principal value. So a starting value here that is $100. The original value of a loan or investment, whatever, at 2%. So 2% of 100 is $2. And let's say if we're thinking after 1 year, then the final value, total value of that thing, we would calculate like this. So 1.02, and we get our value. So the original amount of money then plus the interest rates here gives us interest dollar value. There's our thing. So we'll have the actual formal formulas for this in a moment. But these are the different parts that we will need. Okay, so two types of interest, two basic types. One is simple interest, the other is compound interest. Simple interest is simple. The I, capital I, dollar value of the interest is based on the principal, only based on the principal. So how much rent do we have to pay on this money? Well, just we calculate it based on what the original value was. The original value never changes. So that means the interest, the dollar value of the interest we pay also never changes, it's fixed. So that means the growth rate of the investment or loan or whatever is also fixed because it's growing at the same rate. So if we put it on a graph, it would just be a straight line like this, fixed growth. Compound interest is different. Compound interest, the dollar value of the interest, it's not based on the original value, it's based on whatever the current value is of the loan. The current value will always be increasing, so that means the dollar value of interest that we have to pay also varies. It increases as we go. So the growth rates can vary. Excuse me, it grows. So if we had this on a graph, it would do this. It would curve upward. So compound interest, we pay interest on the principal plus all the previous interest that was gathered. So the interest from 2 years ago and from 1 year ago, that gets added to the total amount. We have to pay even more interest on all of that also. So those are the two basic types. We'll go through a little kind of exploration of what this does with the numbers, and then we'll look at the formulas. So let's say we have, it'll make more sense once we look at some practical examples of these. So let's say we have a person with 2 different credit cards, card A, card B, and they spend $1,000 on each card. And they don't pay off the debt. They just spend $1,000 and then don't touch them. So just there's debt growing on that. So they're not paying off the debt. The first card has 15% simple interest, and the other card B has 15% compound interest. So we want to see what will happen to the value of the debt, the amount owed for the first 5 years. What pattern will we notice? Too hot? Yeah, I turned the heater on. I don't know if I'm feeling a bit hot too. Okay, so we'll look at each of these and see what happens. First, let's just pull out the main numbers. What is our I, our lowercase I here? So 15%, so we'll write this as a decimal 0.15. What is our P, our principal?
1,000.
1,000. Okay, well, we'll consider them independently. We'll compare what happens. Okay, and we have our T value, which is 5 years. The second card compounded annually, which we'll see later, is kind of an important thing to mention. All right, so simple interest first. We have our principal. So principal is 1,000. What is the value after 1 year? So it's
1,150.
Okay, so well, with simple interest, the easiest way to think about it is just adding some value. So it's 15% of whatever this original is. So our I value, write this down here. I value, the dollar value of the interest is 150. And that's going to be the same every year. So that's plus 150, which equals 1,000. So for the second year, sorry, not 1,000. 1,150. For the second year, we have the previous year's value, 1,150 plus 150 again. So 1,300. After 3 years, we have the amount after 2 years, 1,300 plus 150. So, all right, we can kind of see the pattern happening here. After 4 years, after 5 years, I'll just skip some of the writing. 1,600, 1,750. Of those two sequence types that we saw, arithmetic and geometric, which one does this resemble? Arithmetic. So we have this D value here. It's a common difference. Each time we're just adding 150. So it is an arithmetic sequence, and we'll see that with the formula for this in a moment. Okay. Let's look at the other type here. Compound. So here as well, our principal we are starting at 1,000. The I value, though, the dollar value of the interest, remember, it will vary for compound interest. It's going to get bigger each year. So kind of what? We'll have to figure it out separately for each year. All right. So after 1 year, the value of the loan. Okay, so that's the easier way of thinking about it. So times 1.15. This will give us the original amount plus the interest on that, also 1,150. In the second year, things will get different. So 1,150 times 1.15. Okay, so with this example and the next two, if you want to use a calculator to figure these out, that's fine. Interest rates, it's kind of impossible to have the numbers work out nicely and also be realistic. So if we want a calculator, that's fine. What's our next number here? 1,322.5. Okay, so after 3 years, same thing, 1,322.5 times 1.15. All right, we need that number. We need the next number and a 5. All right, who can tell me these next numbers here? Okay, wait, a little slower. 1,520. Okay, round up to 8. All right, next one. 49. 0. Okay, so we'll round that up to this 1. And final number. All right. 2,000. Well, okay, we're missing some decimals. Just that's fine. Approximately 2011. So what kind of sequence does this resemble? Compound interest. Geometric. So this is the R value here. We are multiplying by the same thing each time. All right. So look at the dollar values here. The final value of the loan. After 5 years on simple interest and 5 years on compound interest. We can see the difference there. Does that seem like a significant difference or not so big of a difference? So, okay, the way to be considering this is compared to the original value. The difference here is 25% of the original value. That's really big. Imagine you borrowed $100,000 to get a down payment on a house. After just 5 years, the difference here would be $25,000. So 25% of the original is a very large difference. Little life lesson here. 2 things. First, in these examples, we use 15% interest on a credit card. Is that realistic? Is that too low? Is that too high? Okay, you're right that it's too high, but sorry. It's too high from what we would want, but realistically, this is a low number. Average interest rates on credit cards are more like 17% to about 20, So if you have a credit card, also credit cards are what kind of interest? Compound, always, always, always compound interest. If you find a credit card that has simple interest, tell me, I want it too. Okay, they are always compound interest and it's a high rate. So credit card debt can grow very quickly. Okay. All right, so that's the main kind of exploration here. The only difference, the interest rate was the same. The only difference was the type of interest, the way that we add on the interest. Within just 5 years, it makes a pretty big difference in the value. So type of interest is quite important. Let's look at the actual formulas here. So for simple interest, the so total value is principal plus the dollar value of the interest. Dollar value of interest is just the principal times whatever the interest rate is times however many years. So we put those two things together and we make this formula. So simple interest after X whatever number of years, principal times 1 plus I t. Nice simple formula here. So let's use that formula for the same credit card example, except after 10 years. What would be the value of the debt after 10 years? So A10 will be equal to 1,000 times 1 plus 0.15 t, which we say is 10. So here, 1,000 times 1 plus 1.5, 1,000 times 2.5, 2,500. All right, so that's simple interest formula. And the other type, so take a careful look at this formula and now this one. What's different? The t. So the t is now an exponent and it is outside the brackets, not inside the brackets. Otherwise, same formula. All right, so same thing. We'll calculate the value of that credit card debt on compound interest after 10 years. So A10, 1,000 times 1 plus 0.15. I'm just going to write 1.15 and to the exponent 10. All right. So again, this number pretty annoying to calculate by hand. Can someone use their calculator and help us out here? Your flashlight is on your. $4,045.6 and probably some more in decimals. Okay, so there is the value of this after 10 years. So compare also again the simple interest to the compound interest here. On simple interests after 10 years, the value went up from 1,000 to 1,000 to 2,500. On compound interest, it's gone up to 4,045. So big difference again between the two. If you are, let's say, you're a young person starting off in life, you just got your first job, you probably have to take out loans for a car, for a house, or whatever. What kind of interest would you prefer to have? Simple interest. That would be very nice. If you're older, sort of like your parents' age, and you're getting ready for retirement, you have these investments and whatever, you're saving money, compound interest would be much nicer. So anytime you're in a situation with interest, ask. Make sure you know the exact terms and what kind of interest you are dealing with. The values, the dollar values and difference here are very large. All right, so these are the two formulas. Things always go so much faster with your class. Okay, so we'll go through this example first. Simple interest, it's pretty simple. We're just adding the same number each time. It's like the arithmetic sequences. So we'll spend a bit more time on compound interest instead. So here's the situation. There's the formula. Trying to calculate these two things. Simplify as much as you can, but if you need to use a calculator, or you will need to use a calculator for the last step, that's fine. All right, let's take a look. So before we get to that, first thing I'm noticing here is this word annum. What does that mean? Year. So annum means year, just like the word annual. That's where that's coming from. Annum is the Latin word for year. In normal English situations, we never use this, but investment people and banks do use this. I don't know why, but they do. So good to know that one. All right, so information that we have here for parts A. What information have we been given? Okay, so our original value, our principal here is 5,000. What other information do we have? Interest. Okay, 0.08. Anything else? Our T, our time. is 3 years. All right, well, if we look at the formula, we have 3 parts and we are being asked to figure out if we invest this for 3 years, what would the value be? So that's very doable. We just put everything into our formula. So a 3 here is 5,000 times 1.08 to the exponent 3. And yeah. Sorry, one more time, 6,000. 300. 0.5. Okay. Okay. So about this much. So about 6,300 here. All right. The other part of this. For part B, what are we being asked to find? All right. Okay, so we're given I is the same, 0, 8, T, we are given that as well. What are we being asked to find?
P.
Okay, P, so we have to kind of read the situation carefully. It says present value. What does present value mean? It could mean some investment from the past and it's grown to a present value. It could mean we're starting now and we're talking about some future value, but the rest says needed to reach this much in 3 years. So the other part tells us, okay, by present value, they mean principal. So we're starting now. So that's what we need. So A3 is 15,000 and B is something. So we just put all the parts into our formula. 15,000 equals P times 1.08 to our exponent 3 here. And if we rearrange, P is then 15,000 divided by 1.08 exponent 3. And our number there, 907. Okay. All right. So we can say, well, if we want to reach this value with our investments in this much time, where should we start? Or how much money do we need to put in? Well, that much. Okay. So with our formula, there are 2 more parts, obviously. There's also interest and there's also time. If we have been given the rest of the information, it is possible to calculate the desired or necessary interest rate. So I have this much money now. I want to have this much money in the future. I have this many years of investment. What interest rate do I need? We can calculate that. And we can also calculate for the exponents. So here's my starting point. Here's my desired finishing point. Here's an interest rate with some fund that I can't change. So just how many years do I leave this money in this investment? We can solve for that. We need some fancier math tools, logarithms, to solve for that one. So I will go over some examples with that in the workshop in that we will have this evening. So these 2, solving for interest rates, you need roots. You just always will need a calculator for this. For solving for t here, you need logarithms, which is a bit beyond the scope of our class. So I will show that in the workshop, but it's not like official class content. I'm not going to put that on a test because it's a little beyond what we're doing. But if you're curious and want to see how to do that, I have this example, but instead of doing this in class, we'll do this in the workshop. For the simple interest formula, it's very easy to solve for the interest rate or time. We don't have any fancy math things happening. But for compound interest, it's a little more complicated. Okay, so with the remaining time that we have, yeah, okay, I'll mention this quickly here. So we talked about simple interest and compound interest compounded annually in a finance class or an accounting class. This is going to go a lot deeper, and they will show you how investments could be compounded many times a year, and then there's the formula that would handle that. Or they can also be compounded continuously, and there's a separate formula for that. And then lots of stuff you can do with that. Debt repayment schedules and annuities and lots of stuff. So we're not going to go into all of that. Again, that will be in some finance class later. Okay, so with our remaining time, I want to just quickly talk about slopes. We did this back in week 2 when we saw our formulas for calculating slopes and everything. Let's just see if we remember that. Slope is what over what? Delta y over delta x. Or change in y over change in x. It's good though, so we have this formula for it, but it's also good to be able to just kind of look at a line and see what the slope is approximately. So right now, if I show you this one, can you tell me what the slope is? All right, so it's going to be positive, yes? Is it what kind of number? A really large number, really small number? 1. So this is just positive 1. So it's exactly 45 degrees. That tells us it's going to be 1. What about this middle one here? 0. So it's perfectly flat line. Our slope is 0. What about this one? All right, so it's a negative slope because it's going down, and also so it's -1. Perfectly vertical. Okay, so this is perfectly vertical. It's just undefined. If we got very close to this, it would be, or let's mention that here. Let's say I had another slope, something like this. So also positive. Is this going to be a very large number or a very? Okay, so this one will be a small number. It's somewhere between 1 and 0. Okay, what about this one here? 1 and infinity. So this is approaching infinity. So this will be greater than 1 here. So we should recognize things that are steeper than this. Okay, more than 1, a larger number than 1. If it's shallower than this, it's getting closer to 0. This is perfectly 0. Something like this would be just a little bit negative, but not quite -1. And things like this, very steep, would be like approaching negative infinity. So -10, -20, or something like this. So just visually. What we will do in our next class, not this part, but all right, this is where we're going. This is the core idea of calculus, not just for straight lines, but even a curved situation. we should be able to pick any point on the line, like this one, or this one, or this one, and not say exactly what the slope is, but at least know it's positive or negative, and like a big positive number or a really low positive number. Where does it switch the slope from being positive to negative to positive? That kind of pattern. Visually recognizing that is very important. We will use our calculus tools, and we'll see how we can use that to see exactly where these changes are happening and exactly what any one of these slopes is at any one of these points. But visually recognizing, okay, it's about this much is very useful. And if you're not able to do that, the calculus stuff kind of won't make sense. So what else? So this kind of thing, just looking at a line and saying right away, positive, negative, big number, small number, 0, undefined, just very quickly saying that will be a very core skill for us. All right, last, I'll just do our wrap up discussion, and that'll be it. So calculating simple interest, compound interest, we can do that. That's possible now. We have those two formulas. And that now gives us 9 different formulas for these sequences and series. If you want some example questions to work on, as I've mentioned before, our textbook is not really a finance or accounting textbook. So it does have a few questions about these, but they're not, doesn't go too deep in them, but there are a few examples. Homework question, I have that posted already. There are kind of some details. I didn't want to post them here because you sort of need all the details to make sure you're doing them correctly. So please read that carefully. And the preview question, this is what we will do with the calculus stuff. So we'll be looking at these kinds of curves, doing various calculations with these. So I want you to look at these and try to just, again, visually recognizing a slope. For each of these, where is the slope closest to 0? So look at the x-axis, and tell me the number on the x-axis, whatever it is, where the slope of this total revenue one is closest to 0, and the slope of this total cost one is closest to 0. So you can write that for the homework. And the second thing, so that's visually recognizing slopes. Second thing, when we looked at the break-even points, our total revenue, total cost lines were just straight lines, right? They're very simple, but in a real world business case, they're more likely going to be curved like these. So try to explain how, for total revenue, for example, how we would get this curve. Why does total revenue not just increase forever? It goes up, but then it goes back down later if our Q value gets bigger. So not a math explanation, give me a real world situation. So real world, what things happen that would make a curve like this occur? And total cost, sometimes total cost goes up, but then it kind of goes up by less and then up by more again. What could give, what real world situation would result in this kind of curve happening here? So we'll talk about why in the next class, but I want you to start thinking about that now. All right, that's it. So slopes, limits, all just getting ready for calculus for the next week or week and a half, and actually calculus. All right, that's it. If you have questions, hang around and ask. Otherwise, I will see you guys on Tuesday next week. Goodbye.